Hello everybody and welcome to this webcast on Biomechanics and Computer-Aided Ergonomics. My name is Rasmussen and I was recently appointed Professor of Biomechanics in the Department of Mechanical Engineering at Aalborg University. And this webcast is a slightly modified version of my inaugural lecture that I gave a couple of weeks ago. Usually we don't do much by way of introduction when we do these webcasts, but since this is an inaugural lecture, I thought that I would just say a few words about the career moves that I have made. I was born in 1963, so those of you with mathematical inclinations can figure out that I am 44 years old now. And I got my master's in mechanical engineering in 1986 and proceeded to do a PhD where I worked with design optimization based on finite element methods, and I completed that in 1989. Now all of this was completely and solely based on usual mechanical engineering, so there was no bio in the picture at that time. I proceeded on to become an associate professor in 1992, and somewhere in the time following that, I got together with a good colleague of mine, Michael Damsgaard. Michael is an expert in multibody dynamics, and we were at the time looking at problems of designing bicycles, and we had some students that we were supervising who had an interest in modeling not only the bicycle but also the bicycle rider. And during a coffee break one day we came up with the idea that if we combined what he could do in multibody dynamics and what I could do in optimization, we might be able to bring the field a little bit further. At least we thought we had some good ideas. And this led up to the formation of what we now call the Anybody Research Group. It began around 1997, but of course these ideas were stuff that were tumbling around in our heads for a while before that. But in 1997 we got funding, and we were able to formally establish the group. In the meantime, I also ventured a little bit into the business life, in the sense that I formed a company called Rational Engineering in 1991. And this company was dealing with finite element analysis and in particular with design optimization. So we were doing various simulations on machinery and other structures that we were trying to improve by means of optimization. That went quite well actually, but at some point we thought that we wanted to do something new. So we closed the Rational Engineering company and we proceeded only with biomechanics. The Anybody Research Group then had a spin-off company which is called Anybody Technology, and this was formed in 2002, and Anybody Technology is actually the company that is now the host of this podcast. And then recently in 2007 I was appointed full professor of biomechanics at Aalborg University, and this is very nice, of course. It is a clear sign that Aalborg University thinks that biomechanics is an important field, and that they are willing to invest in the field, and that they also give priority to the importance of biomechanics. And of course I think that is a very wise move. And, another way of seeing the career moves is that I have gone from mechanical engineering into computational mechanics at a time when everything had to be computational, and so I was sort of following the trend, and I think that now I have moved into computational biomechanics, and I think actually also there is a trend that the bio field in general is coming up and is becoming more and more important. And there's a lot of work for mechanical engineers to do in the bio field, and I hope that I can contribute a little bit to that. Most of what I do is about a concept called Anybody. And Anybody is actually many different things. But if I can give you the general idea behind it, it is actually a very engineering-oriented undertaking. The whole idea is built on basic engineering disciplines, namely principles of equilibrium and other good stuff. And it's actually illustrated by the figure that you see in front of you. Now you can see that this is a forearm that's carrying a certain load. The gravity on the load amounts to 49 Newton. And then there's a certain self-weight of the arm. And if we set up the equations for the equilibrium equations for this system, then it is actually very, very easy to figure out that given equilibrium in the system, the muscle force, the Fm force, must be 382 Newton. Now there's a couple of things that we can derive from that simple exercise. The first thing is that the 382 Newton is actually quite a bit larger than the applied load, the external load of 49 Newton. And this is pretty typical for our bodies. The loads inside our bodies are actually are higher than most people usually think, and this is because the moment arm of the external forces when they are acting on our limbs are usually larger than the moment arms of the muscles that are counterbalancing those loads inside our bodies, and therefore the forces in the muscles have to be larger than the forces of the external loads. There's another thing we can learn from this, and that is that the human musculoskeletal system and biomechanics in general, although it seems very complicated, actually, as everything else in this world, must obey the laws of physics. And you can see that the laws of physics, in this case, very nicely give us a way to compute what the force is in the muscle. And actually, everything that we do in the Anybody group is based on this idea. We are a very basic mechanical group, and we are applying the laws of mechanics to biological systems, and we are trying to see how far we can get. If we look at the next picture that's coming here, then you can see that the same principle applies to more biologically realistic systems, except for a couple of changes. One of the changes is that we don't have just one muscle. You can see that we have many muscles in this arm, which is pretty much the same situation as the one you saw before, only this one is more anatomically realistic. And but because of the many muscles that are present here, the mechanical system becomes much more complicated than the one that you saw before. And we cannot handle this by means of analytical equations on paper. We need computers to handle this mechanical system. Another complication is that we have multiple degrees of freedom here. We don't just have one elbow and one angle in the elbow. We actually have many degrees of freedom and many joints in the system. And we also have closed chains in the system. For instance, the shoulder girdle is a closed kinematic chain. And those of you who have experience with analysis of mechanical systems know that closed chains tend to complicate things a bit. And all this means that it's impossible to compute these systems by hand. You really have to use computers to get the forces inside the systems. Another thing we can see from this is that in addition to the software and the computers, we also need reliable models. And you can see that the muscle configuration on this model is quite complicated. And therefore, developing these muscle models is a big task. So there's a lot of work to do. But when we have done that work, there's an enormous potential. And in this presentation, I will try to outline some of that potential, and I'll also try to give some of my views on how we can exploit the potential. So I'm going to try to make a couple of, actually 3 different points in this presentation. The first point is here. The first point is that ergonomics and medicine are going computational, and this is something that is completely new. It's a change of paradigm. The fields of ergonomics and medicine and physiology, if you will, have always been founded on empirical investigations. They have been founded on the urge to watch how nature is behaving and draw conclusions from that. And by means of these mathematical and mechanical models, we're able to take this one step further. And instead of just watching nature and observing how it is working, we are able to derive some salient qualities of the systems, and we are able to set up analytical equations and mathematical models, and we're able to draw conclusions from those. So the whole field is changing from being an empirical field to becoming an analytical field. You could also say that the engineers are really moving in. This also means that instead of making qualitative conclusions, like if you don't stand properly, then you are going to get a problem with your back, or if you don't lift the right way, or if you don't change position or whatever, then there's going to be some sort of problem. Now that would be a qualitative statement that isn't always very accurate and isn't always even true. But with these analytical methods, we are able to become quantitative instead. So we can make statements like, if you move the load 5 centimeters in one or the other direction, then you're going to change the load on your spine by so or so many percent. And these quantitative informations are much more valuable because they give you tendencies in the way you try to change the environment. And it can give you a lot of information about that you can use to design the environment or design implants or do other sorts of stuff that you need information about the musculoskeletal system to do. So in general, this opens up a whole lot of new opportunities, and this is what we want to try to exploit here. Now, computer-aided ergonomics in a nutshell. What you may have seen here was a video. I'm not sure whether the video actually makes it through the transmission speed from the internet. I guess it depends a little bit on how far away you are. But if you're on a fast connection, then you should have been able to see that the figure on the right was actually moving the handle around one round, and you may also have seen that the muscles were bulging in response to that movement. Now, I didn't let this continue playing because with these webcasts we have an experience that if we send out too much data into cyberspace, then it sort of tends to block up the communication lines, and we don't want to risk that. But when you have a mechanical model of a case like this, then you can get as output from that mechanical model all the forces in the system. So that could be individual muscle forces, but it could also be the joint reactions. And if we do this, if we run this model and we plot the reaction in the glenohumeral joint, then you get the graph that you see on the left. So those are the reaction forces in the glenohumeral joint. And you can see that there's a peak in the middle. Maybe I can set up my mouse here to mark it just a second. So there's a peak in the middle of this movement, and that is actually when the arm is retracted and trying to push the handle outwards laterally from the body. That is kind of hard to do, and the muscles have very poor moment arms for doing that, and that then results in a high reaction force in the joint. And if this is a repetitive working movement, working process, then of course this high peak in the joint reaction forces might lead to some sort of problem with the shoulder joint. And now let's say we have a person who is doing this work task and who is experiencing a problem with the shoulder. So the person is complaining about shoulder pain. Then what would you do in order to alleviate that pain? How could you redesign the workplace here so that the pain doesn't happen? This is a kind of difficult problem because it's very difficult to measure forces inside the joints. So the only way that you can really do this is to simulate it by computer. And this is then what we're able to do. And then in the computer model, we can start moving the handle around compared to the position of the body. And we can change the length of the arm on the handle and so on. And then we can, by playing around with these parameters, we might be able to find a position which is more suitable and which doesn't cause large peaks in the joint forces. Now, this is really in a nutshell what you can do with computer-aided ergonomics. Here's another example. And again, I wish I could show you a video, but I've chosen not to do that because of the transmission speed. So you can see the figure on the right is pushing a bed. And this bed can be pushed by means of a handlebar, and the handlebar can have 3 different heights. And the question is now, if the person has elbow pain and wants to protect his or her elbows, then which height should the handlebar have? When I ask audiences about this, I get roughly 33% guessing on each position. And now you can make your own little guess while I continue talking here. But my point is actually that it is pretty difficult to see. When I give you the result in just a moment, I'm sure that you will say, oh yes, of course it's like that. But it actually turns out that the high position of the handle is the best, at least in terms of muscle effort. So if we look at the muscle effort that we get, which we have over here on the second axis of the graph, and then we have the movement on the first axis, and then you can see these 3 graphs. Those are the muscle efforts in percent of maximum voluntary contraction of any muscle in the body. So this is the envelopes of all the muscle activities. And you can see that the lowest envelope is when we have the high location of the handle, and the highest envelope is when we have the low location of the handle. So if you were guessing that the low location of the handle would be the most comfortable, then try to imagine that we turn the whole situation around. So we rotate the person 90 degrees, so he's lying on the floor. And then pretty much the movement he's doing here corresponds to a push-up. And so if you were to get down on your belly and do a push-up, you probably wouldn't put your hands low. You would put your hands at shoulder height. And this is the reason why it is easier to push the bed when the handle has a high position. If we look at the elbow forces, which were really the issue here, we get pretty much the same results. Here we have on the second axis now the elbow joint forces in Newton, and you can see that we have much lower elbow joint reaction forces when we have the high location of the handle than we have when we have the low location of the handle. In fact, the forces are only half with the high location of the handle. So I guess my point here is that after you see the result, you can very often understand the reason of the result, but before you see the result, it's very difficult to guess. So computer-aided ergonomics really allows you to get some ideas about the tendencies of the parameters that you might want to vary, and you can make decisions based on that are much more safe and much more qualified than decisions that you are making entirely based on qualitative information. Now here's another example, which is about rehabilitation of the Patella tendon, and again I wish I could show you the video. It's a really cool video of a person doing a squat movement. This movement has been recorded by a motion capture system, and then it has been imposed on the model. You can actually see these little dots here. Those are the motion capture markers, the optical motion capture markers, and they are driving the model. So what the model does is it puts the weight on the right leg, and then it squats down, and then when it has squatted down, it moves the weight of the body to the left leg, and then it extends the knees again. The reason why this is done that way is because it turns out that patella tendons that have been injured, they can be rehabilitated faster if you load them in eccentric loading. So the people who have done this example, and this is actually Kjartan Halvorsen from the Sports Academy in Stockholm, they are interested in designing exercises that will verifiably load the tendons in eccentric loading. And so he was able to verify by means of this model that the exercise had the desired effect. Now here comes the second point. My second point is that if we want to exploit this technology to its full potential, then it is important that we separate the task of making models from the task of making software. And why is that my opinion? I will try to get back to that one. Well, obviously, in order to be able to do this, we need good software and we need good and validated models. The problem here is that it's not easy to make both of these the same place. Now, I have tried for many years now to make software at the university, and I've always had the ambition that the software that we made, whether it was finite element software or multi-body dynamic software, should have a quality that was at least semi-professional so that other people would be able to use it. I've always been appalled by the enormous waste that there is in the scientific world, in the sense that lots of good work is taking place that never make it out of university offices. And at the same time, you have people out in society who are, at the end of the day, who are paying for the science and who never get a chance to exploit that technology that is being developed. So technology transfer from the university to real life, if I may call it that, has always been high on my agenda. Now the problem is that it's very difficult to develop good software at a university. And the reason why this is difficult is that good software requires a certain quality of user interfaces and a certain testing and version control and a whole lot of logistics around the software production process. It also requires manuals and support and download pages and a whole lot of other things which are very difficult to do and very time consuming and expensive to establish, but which are really not research. And universities usually don't think that it's a very good time that we spend research money on making these infrastructure things. So universities are not a good place to develop software, and therefore it's important that we find somewhere that we can develop the software. We also need good and validated models, and the model development is something which is actually very tricky and very time consuming. And it is not completely known how we should make these models. There's a lot of biomechanical work being done, and you can find references to most of it when you look at the models that we have made, because we're stealing all the models we can get our hands on. So there's a lot of very, very good biomechanical research work being done simply on figuring out how to make good biomechanical models. And all this is very valid and very worthy research tasks. So this is well placed at the university. But it is not a very nice thing to, or a very easy thing to do in a company. And there are several reasons for that. One is that companies have to make money, and developing these models take a very long time. Another reason is that the models have to be validated. And well, the companies could do the validation, but the validation that the companies are doing probably would not have the necessary credibility, because obviously the company is interested in showing that their model is working well. So in order for these models to be validated and verified, we really need to take this through the established scientific system, where independent scientists have the opportunity to scrutinize and criticize the models, and we need to go through the peer review process of the publications we make and so on. All this is very well placed, not in a company, but in a research environment. So we need to take the software out of research environment, and we need to keep the models inside the research environment, and therefore the two must separate. Final reason why we must separate software from models is that we think that we should, in the way that we develop this technology, we should look at similar technology that has been made before. And all these technologies go under the common name of computer-aided engineering, and the most prominent example of such a technology would be finite element analysis and maybe computational fluid dynamics. Now, the typical way these systems are built is that the systems are modeling systems. So they are systems in which the user builds a model. When you open a finite element system, there is nothing in it. It is actually completely empty. And then it's up to the user to make a model. So why didn't we put a model inside those finite element systems? Well, the reason is, of course, that it would be impossible to foresee for the programmer all the different types of models that people might want to analyze in a finite element system. And therefore it's impossible to pre-equip the finite element systems with such models. So instead they have facilities for building models. And the same thing goes for musculoskeletal analysis. I know that there are digital mannequin software out there that has a human model built into it, and you can scale it up and down and so on. But I still maintain that when you want to calculate forces, it's impossible to foresee all the types of models that people might want to do. Because the mechanical system is not just the human body, it's also all the devices that you hook the human body up to in the environment. It could be bicycles or chairs or car seats or workplaces or simply a floor that the person is walking on, a force plate, whatever you name it, any sort of working situation that you can put the human body into. You need to model not just the human body but also the environment. And it really, really is impossible to foresee all those different types of environments. So therefore, we need to develop these systems CAE style, in such a way that the software is separated from the models, and the users have the opportunity to build models inside the system. And all this is the reason why we need to separate models from software. The solution that we have made in the Anybody undertaking, and when I say undertaking, I mean everything that's involved in all the Anybody stuff, it is that we have separated into two organizations. We have on the one hand Anybody Technology, which is a company. And Anybody Technology is responsible for development of the Anybody modeling system. So Anybody Technology is a software development company. And by putting the software development into a company, we're able to solve those problems of making manuals and documentation and version control and all that. We can probably do it much better than we do, but at least we have the opportunity to work seriously with that. On the other hand, we are placing the AnyScript model repository. This is the models that we are developing. Those we are developing at the university in the Anybody Research Project. This is public science that is being made for public money at the university, and therefore the AnyScript model repository is entirely in the public domain. And when I say entirely in the public domain, I really, really mean entirely in the public domain. There is no strings attached to these data. You can go to the homepage of the research project and you can click on a link and you get the entire model library downloaded to your computer. You do not need to register. You do not need to tell us who you are. There is nothing you need to sign. There are no license agreements. There is no user agreement. There's no disclaimer. There is nothing. You just grab it and you do with it what you want. It really is in the public domain. So the model repository, the AnyScript model repository, is something that we are investing a lot of our research activity into. It has taken a very complete nature. You can see a picture of the human model we have in the repository on the right-hand side. It's a rather complete model. It has more than 500 individually actuated muscles in the model, and it covers almost every important part of the body, with the notable exceptions of the cervical spine, the thoracic spine, and the hands and the feet. But the remaining parts of the body are actually all there. And those parts that have not yet been developed, those we will develop in the forthcoming near future. There's also work going on development of different animal models, and those will also be a part of the repository in the time to come. We have come up with a way of making the model scalable. We actually have built scaling into the model, so you can scale the same model to become small or large people, or males or females, or high and thin people, or short and squat people. You can scale it in every dimension, and you can scale it on an overall level, and you can scale it on a segment level. As I said before, this is open source. This is completely public domain, and it is also there's also a suggestion of a structure for the musculoskeletal part of the physiome. Now, the physiome is a hot topic at the moment. The musculoskeletal, the human physiome is an undertaking that is actually going on in many different parts of the world today, and it is an attempt to make a data structure in which we can collect all possible information about the human physiognomy on multiple scales, so ranging from molecule structures to overall properties like entire muscles and an overall structure like you see here. The Anybody research group is not trying to tackle the entire physiome project, because that would be much too much for us. We are concentrating on what we think we're good at, and that is to do the musculoskeletal part of that. But the structure that we have built into this library actually allows many of the things that people will want to do with a physiome. Namely, it allows us to take different parts of different models and hook them up with each other. The language we have developed that represents these models is capable of making interfaces between the different body parts, and it is also capable of handling stuff like mirroring from one side to the other, and scaling of muscles, and a whole lot of other stuff that we might want to put in. I should also say that even though we work hard on validation, this is only partially validated, and it will always remain only partially validated, because it is impossible to validate these models in every conceivable situation that you might want every conceivable working situation that you might want to put the human body into. So the validation process is actually an open-ended activity, but we are putting a lot of effort into that. Which brings me to the third point. And the third point is that if we want to realize the potential of this technology, then there has to be international cooperation between scientists, and there also has to be a cooperation that involves the industry. Because if the industry is not involved in this, then we will never bring this technology out where it actually does something good for society. And let me show you a couple of examples of industrial projects that we have been involved in. Now, the first one is with the automotive industry. We have a lot of interest in what we do from the automotive industry. I think this is because the automotive industry is the largest and most advanced industry in the world. So they are capable of assimilating technology like this at an early stage. One of the things that the automotive industry is interested in is the aging population and the problem of getting in and out of vehicles. This is also called ingress and egress in the automotive jargon. The issue with elderly people is that they have limited muscle strength compared to their body weight, and also that there's a high prevalence of arthritis in the knees and in other joints, but particularly in the knees. If you take people above 60 years of age, then more than 90% of them have some signs of osteoarthritis in the knees. So one of the things you can do to help people get in and out of vehicles is to place an assistive handle on the window frame. And this is what you see on the right-hand side here. And this assistive handle can be put at different positions on the window frame, and we simply want to figure out which one is best. Should we have the low position or the high position, or one of the two positions in between? You can think a little bit about that while I change to that. Because on the next picture, you can see here the movements that we have imposed on the model. The movement begins with the posture you see on the left-hand side, where one leg is on the curb, and the other leg is inside the vehicle, and then one hand is pulling on the assistive handle. The other hand is presumed not to do anything, so it's just sort of hanging out in the air here. You can see the movement on the overlay pictures on the right-hand side, and you can see that it's only kind of the middle part of the movement up until the person is nearly standing and is going to take the right leg and take it out of the vehicle and put it again on the curb next to the left leg. So it's only the part of the movement where we have constant boundary conditions that we have analyzed here. Then here comes the result. What is best, a high handle or a low handle or something in between? Well, if we look at these graphs, what they say is that in terms of muscle activity or effort of getting out of the vehicle, the high handle position is preferable. And I guess most of you probably guessed that that would be the case. The way you can see that is that the high handle is the one that's called 0.3 here in the legend, and this corresponds to the low curve on this figure. And you can see that this low curve is the one that has the least amount of muscle activity compared to maximum voluntary contraction. And this only reaches up to 70% of the body strength at the maximum to get out of the vehicle. And you can see that if we use the low position of the handle, then we have significantly more muscle activity to get out of the vehicle. Then what about the knee forces? The knee forces would be determining the amount of pain that people with arthritis in the knees would feel while getting out of the vehicle. Found actually that the difference between the different handle positions is much bigger when we look at the knee forces. And you can see that again the low position of the handle is not very preferable. You can see that with the low position of the handle we have a high peak of knee forces in the middle of the movement, whereas with the high position of the handle we have a sort of almost constant force in the knee during the first part of the movement, and then they all taper down at the ends when the person gets up to nearly standing posture. So this pretty simple investigation very quickly gives us an idea not only that a high position of the handle is the best, probably we could have guessed that also by simple subjective investigations, but it also tells us something about how much better is the high position of the handle. And that quantitative information is really important when you are designing something as complicated as a vehicle. Another industrial example is from the furniture industry. This is the company RBM that manufactures office chairs, and we have a lot of cooperation with this company. One of the issues in seating, in design of office chairs, is the forces in the low back, and those are illustrated here. You can see here an illustration of the forces between the L5 and the sacrum, and we are interested in how different designs of the chairs influence the forces in this joint. And I'm going to show you another video, so please stay alert of the picture that comes when I push the button again. I hope that made it reasonably well over the transmissions. If you didn't see the movement here, then I can tell you that what happened was that the person was forward inclined in the beginning and did not have contact with the backrest. And then the back was inclining backwards, and at some point it came into contact with the backrest and started pushing the backrest back to a more lean back position where we see the body now. And exactly at the time when the when the upper body hits the backrest, we can see that there is a drop in the forces between the L5 and the sacrum, in the compression forces. And so here we can see exactly how much is the benefit of having a backrest. So if a person is complaining about back problems and is working in a forward-seated position for a very long time, then in this particular case, it might be a good recommendation to recommend the person to once in a while sit back and rest a little bit on the backrest and take some of the pressure off the lumbar spine. Another issue with office chairs like these is the stiffnesses of the springs that are embedded into the mechanisms of the chair. And that's what we can see on the next investigation. As you can see here, this is a slightly different model of chair where the seat and the backrest are moving independently of each other. And you can see on the left-hand side an initial position which is sort of upright sitting, as it would be when you were typing on your computer. And you can see then a resting position on the right-hand side. And again, ideally, we would like to come to a resting position that would take some of the load off the spine. And we are here investigating the influence of the spring that is embedded into the mechanism and which is causing the backrest to push back on the upper body and thereby support the upper body when it's leaning backwards. Now there are three cases here. The first case is the red curve, and the red curve shows what happens if the spring is too weak, meaning that the spring is so weak that it doesn't properly support the weight of the upper body when you lean back. If that is the case, then you have to employ muscle forces to keep the upper body up, and this causes an increase in the compression of the spine. And then you can see that actually the further you lean back, the more force you're getting in the spine. So having a too weak spring is not a really good idea. The black curve is the second example. That is when the spring is too strong. You can see that in the beginning when you lean back, that goes quite well. We reduce the forces in the spine, but then when you lean far enough back and the spring is getting tense enough, it will start pushing more back on the upper body than the self-weight of the upper body. And then you need to, again, engage muscle forces in pushing down the backrest, and this causes the forces in the spine to go up quite dramatically. So again, a spring that is too strong is not a good idea. On the other hand, it is possible to find a near optimal spring which will give you a uniform low spinal compression when you lean back on the backrest. So I guess that the message here is that it is really important that you adjust your office chairs properly when you are sitting on them. Now, I talked before about how we can get this technology out into real use and have people design real chairs and real cars and real medical devices and so on with the technology and thereby improve the lives of people. Now, real technology, even quite cool technology, sometimes fails to really make it out to the majority of the users. And I'm sure I won't mention any examples, but I'm sure that if you think of for instance, the computer revolution, you can think of many technologies that were actually quite nice, but which never, for some reason, never made it beyond the initial enthusiasts that were using them. And that is what this graph is trying to illustrate. It is called a technology adoption lifecycle. And it is thought that in the lifetime of a technology, initially, not a lot of people know about it and not a lot of people are using it. It may be a little bit immature in the beginning, so mostly what we call early adopters are using the technology. Then later, when the technology gets well known and it matures a little, you can get the majority of users, and that is the big bulk there in the middle. And then later, when the technology becomes a little bit too old, some people are still using it, but the use of the technology is fading out. Most technologies are working that way. Of course, the width of this graph is somewhat different for the different technologies. However, the interesting part of it is what we call a chasm, which is here. And the chasm is the fact that some of the technologies never make it beyond the first step. So they get embraced very enthusiastically by what we call early adopters. And they could, for instance, be university people or people who have a special technological interest. in using the technology, and they embrace the technology initially, and they're very enthusiastic about it. But the technology really never makes it further than those initial users, and that means that the impact of the technology becomes very low. And there is a distinct danger that a technology like ours could fall into that chasm and never make it out to the majority market. I think that would be a real pity, because there is a definite potential in using this technology. It doesn't have to be ours, but the whole idea of using musculoskeletal stimulation definitely has a potential which should be exploited somehow in the market. So one of the missions that I have in my professorship is that I'm going to try to help pushing the technology that we have across that chasm. And I will do my best in cooperation with industries to try to bring this out into real life use. And I also internally work with people at my own university and other universities in order to improve the credibility of the technology so that it becomes as valuable as possible. And hopefully we can get it across the chasm. Some of the things that are located in the majority market here would be sports applications, occupational biomechanics, clinical applications, embedding the technology into hardware, for instance, in fitness machines, and also building the technology into CAD systems. And those are all of these are things that are difficult to do, but things that we would like to do in a not too distant future together with different partners. We think that this could help reach this majority market. I'll give you a couple of ideas of things that we could do. The first one you see here is an attempt to do a clinical application based on the technology. Now, clinicians are impatient people because they have patients in their clinics and they need to come up with fast answers, and they cannot mess around with difficult technologies while they're working with the patients. So they need something that gives them answers quickly and works every time. And that means that they have no use for immature technology. Now, it might be possible to wrap musculoskeletal simulation into the kind of environment that you have in a Gait lab. And then you could provide the clinician with feedback on forces in the muscles and in the joints, and the clinician could use this technology to prescribe orthoses or footwear or plan surgical procedures and that sort of stuff. This is definitely one of the things that we would like to do. Another idea is bicycle fitting. This is really for the mass market. Lots of people are driving bicycles and are doing it very enthusiastically. And they are quite interested in figuring out what the optimum fit of the bicycle to a given body would be. And this is basically a biomechanical problem. We have quite good and reliable bicycle models for the system, and in the model repository, and you can employ these models to do a bicycle fit. Again, this might require the technology to have a different wrapping so that it is very easy to employ in particular for bicycling, and this is something also that we would like to do. So we are approaching the end of this presentation, and the three take-home messages that I hope that you would remember from this is that ergonomics and biomechanics is going computational, and it's a good idea to separate the models from the software, and finally that it's important that science and industry work together to realize the potential of this technology. I should also acknowledge a lot of people who have worked together with me on this. I have done very little myself. But lots of people have been kind enough to help in this task, and you can see some of the names on this slide. I won't go into details about it, except perhaps I would like to say that especially we are thankful to those early adopters that have taken the technology at an early stage and who have believed in the potential of this technology and have invested time and effort and money into exploring it together with us. And with that, I would like to say thank you for showing up for the webcast. I'd like to invite every one of you to do scientific cooperation with us. We are very open to doing that type of cooperation. We are a research group, so the purpose of our cooperation is to do science. And if you want to have a tangible result of the science, it is to write and publish papers. So we would like to do that type of cooperation, and we are very focused that it must on the fact that it must end in publications that we can do together. Therefore, we also try to find partners who have complementary competencies to what we can do. In the Anybody group, we are pretty good with computational mechanics, but we don't do a whole lot of experimentation. So we are particularly interested in doing cooperation with people who are experimentalists and who can provide experimental data that we can use to build better models or validate the ones that we have. There's a few other resources that I would like to draw your attention to. One is a Yahoo group. I'm not sure if all of you know the Yahoo group system. It's a system of discussion groups that you can sign up for, and they have a technical section which is called tech.groups.yahoo.com. And inside that system there's a group called AnyScript. And there's a whole lot of members there who are discussing the development of models in our scripting language, and who are getting help on modeling issues using that language. There's a couple of homepages I'd like to draw your attention to. One of them is the anybody.aau.dk homepage, which is the homepage of the research project. On that homepage, you can in particular find our reference list. And many of the papers are directly downloadable from the reference list, but of course the journal papers and such, we do not have copyright for those, so you cannot download them directly from the homepage, but you can go to the respective journals and get them from there. You can also get the model repository from that homepage. It is placed there, and as I said, it's completely open and in the public domain. Then finally, we have the anybodytech.com, which is the company's homepage, the Anybody Technology homepage. And here is where you can get the software. You can download the Anybody modeling system from that page, and you can then go, you can get a free license that will work for 30 days, and you can then go to the homepage of the Anybody research group and download the model library, and you can play around with the models and perhaps make a few of your own. And with that, I would like to say thank you for showing up. We're going to take a break of just a minute or two while we review whether there have been any questions that haven't been answered. If any of you have any questions, then please notice the little question mark in the lower right-hand corner of the screen. If you click that question mark, you will get a question and answers panel, and you can type in a question. And if you do so, I will try to answer it orally here, or some of our supporters who have answered them in writing directly in the question and answers panel. So I'll be back in just a couple of minutes.